Okay, so we've seen thus far in the course a number of thermodynamic potentials. Temperature, in a way, is a thermodynamic potential because it indicates when thermal energy will flow between objects. Enthalpy is another one. Here's a couple more. Free energy, we've already mentioned this, and that measures the availability of energy if we're in a constant temperature process. So if we go down here, we could say that internal energy is a state variable, and then at constant temperature, we would use the Helmholtz free energy as a potential. At constant pressure, we would use our enthalpy. And then lastly, if we have a constant temperature and a constant pressure process, then we'll use the Gibbs function, or the Gibbs free energy, defined thus. And so the Gibbs function, G. So this function here will be used to study spontaneity when we have a constant temperature and a constant pressure process. And one case where you encounter that is during phase transitions. Say if you're boiling water, then that's going to happen, well, at STP, that would be at atmospheric pressure, and it would be at 100 degrees C, or 373 Kelvin, and it would remain constant, the temperature, until the phase change was complete. So we're going to use this Gibbs free energy now to derive a relation known as the Maxwell relation, which is just a connection between entropy, pressure, volume, and temperature. So here's our Gibbs function. We just wrote it down. We'll write it down again. So U plus PV minus TS. So if we do the differential of that, so that'll be du, then we'll have to do this using the product rule. So it'll be P dV plus V dP. And then once again, we'll have to product rule this one, so it'll be minus TdS minus SdT. Now, the first TdS equation tells us that du is TdS subtract PdV, at which point we see a TdS goes away and a PdV goes away. So what we arrive at then is the differential of the Gibbs function is V dP minus S dt. Now we can deduce a couple of things from that. This must be the potential derivative of G with respect to P at constant temperature. So at constant temperature, partial G with respect to P must be the volume, and this must be the partial with respect to temperature at constant pressure. Negative of the entropy. Okay, now what's typically done with these problems is you take the next derivative. So you'll differentiate this one with respect to t and this one with respect to p, and then say those two must be the same. So these are called the mixed partials, and they will always be equal for a continuously indifferentiable function. So derivative of G with respect to P, we showed earlier, was the volume. So replacing, well, this should be like there's missing another one of those, right? So this is going to be the partial with respect to T. dG dP, that was the volume. And on this side, we've got a partial with respect to pressure. And then the derivative of the Gibbs function with respect to temperature is the negative of the entropy. So what we have shown then is known, and we'll need this later when we derive the Joule-Thomson coefficient. This is known as a Maxwell relation, and there are several of these. And they tell us that a relationship again between entropy, pressure, volume, and temperature. And it comes from the second order mixed partials being equal to each other. And that is, believe it or not, our pre-lecture video for today. We've derived this relationship, and there are others like this as well. But we only need this one for today.